So let us quickly summarize what we discussed in our previous lecture. So in our previous lecture, basically we discussed about the dependencies, the different kinds of dependencies, and most of the important concepts have been already covered. In future lectures, we'll again revisit this topic on certain advanced concepts. But the important learning was the computation in one iteration. If the computation in one iteration depends on the result of one or more previous iterations, then we have to be very careful before we can distribute those computations to different threads or different cores. The most important one which we learned was the loop carried dependence and the flow dependence, and one should be able to remove these dependencies. Okay, now today we are going to look into another very important topic, which is about the metrics of parallel computing. So till now we have been talking about the metrics for performance, like megaflops per second or uh, gigabytes or gigaflops per second, gigabytes data, gigabytes per second. So that was more about at what rate you can do computation and what rate you can access data. So that's about performance. So today we'll be looking into something different, which is like the matrices which we use for parallel computing, because the performance matrices are equally valid even for serial computers. Okay, so let's start with a very simple example. Um, So in this first example, we were just having a very brief understanding about how to introduce parallelism in a simple algorithm. So let's say that we want to add n values, okay, and we first want to compute n values and then we want to add them together. So if I look into the serial code, it's very simple. So basically what we can do is like we can always create some serial code like for I is equal to 1 to n, and then if I want to store the result, I can always say ai is equal to some function, okay, and that's the output of that some function. I'm just don't look into the syntax. So what I'm saying is that this function basically gives you an output which is x, and that you are storing it in AI. And finally, if you have to calculate the sum, you will just you do sum plus is equal to this AI. That's all. Now, if you look into the serial computation, we can see that as such, there are no major challenges. I mean, one by one it will be done. So you will basically run this loop n times and you will get the answer here. Now, suppose I have P cores or P threads or P processors, whatever you may call it, and let's say that P is much less than this N. So number of processors is much less than N. So how we'll do this in parallel? So as we discussed in our previous lecture, so as such we don't see any dependencies here. So if you look into a particular iteration, you see that the sum actually when you calculate the sum, it definitely depends on the previous iteration. I mean, because they are related somehow. But if you look into this calculation, this AI, so it does not really depend on anything else. So it is like independent for each iteration. Okay. Now, if I have to design an algorithm for this, a parallel algorithm for this, so one design can be, let's say that I have P processor. Let's say P is equal to, let us just write, let's say P is equal to 4. So one thing what we can do is like we can say that this the first one will do n by 4 additions. Okay, the second one will do n by 4 additions. I mean, by second one means, I mean, this is P1 core, this is P2 core, this is
Sir,
P3. Yes.
sir, again your screen is lagging. Means you're speaking first and
Oh,
then it
okay,
is
okay,
okay.
okay. Just a minute. I mean, that. Thank you for telling that. Once again. Is it better now? I will once again I will write it. So you can see this for loop here, this left
Yes,
side. I'm Yes, okay.
now it is fine.
So now it's fine. Okay, thank you for telling. And whenever you have a problem, just let me know immediately. Okay. So let's say that we have P processors or P cores, and we want to divide this work into into these four cores or four processors. So one simple strategy can be that you give n by 4 amount of work to P1, another n by 4 amount of work to P2, another n by 4 amount of work to P3, and another n by 4 amount of work to P4. And but then it's not done. If you just do that, it's not absolutely done. Actually, you have to do something else. So what additional thing you have to do here?
We have to add the output.
Adding all the output.
Yeah, you have to add the output. You have to add this. So we have to take all the output from here, and then we have to add it. So this is basically P1 plus P2 plus P3 plus P4. I mean the sum. So P1 sum, P2 sum, P3 sums, and P4 sums. Okay. Now, in terms of computations, are we doing any extra computation? Just in terms of computations. So how many
No,
additions you are doing here?
n by
And by
4.
4 minus 1.
Exactly, n by 4 minus 1. That's very important. Okay. Now in this code, in this serial code, how many additions you are doing? So you are adding n numbers. How many total additions you are doing? Total additions.
N minus
Total
1.
addition. Yeah, n minus 1. N minus 1. So here you are doing n by 4 minus 1. So and all the processors are doing that, assuming that n is equally divided by 4. So total, how much you are doing? I can write it 4 into n by 4 minus 1. I can write it 4 into n by 4 minus 1. That is acceptable to all of you. And
Plus
then
3. Hmm.
yes, exactly. This is like this part is like how much by all individual processors, and this part is plus 3. Okay, so this part, if I just look into this part and if I add it here, so I'm getting 4 into n by 4 minus 1, so that makes it n minus how much? N
N
minus
minus 4 plus 4.
n minus 4,
4.
n minus 4, and this plus 3 is coming here. Okay, so this plus 3, so n minus 4 from here and plus 3 from here. So finally you are getting n minus 1.
1.
So here also n minus 1, here also you are in minus 1. So as far as total work is concerned, you are not doing any extra work here. But otherwise, is there something which is extra here in this code? Something which is not present here in this serial code.
Distribution of n by 4 to every processor, then recollection of the data. That kind of
Yes.
work.
So yes. So there are some extra work which you are doing. So the first work which you are doing is like first you are deciding that how much to be given to each processor. Then you are calculating the total work which is required to be done by each processor. And at the end, you are collecting all the results from these processors and then you are adding them. So this part actually requires some kind of communication. All of you agree, right? This part, all of you agree?
Yes, sir.
Yeah. So the point is, although as far as total number of additions are concerned, that is same, absolutely same, n minus 1 here, n minus 1 here. But if I look into it this design carefully, then I can see that I have to do some communications, extra communications. So that is called overhead. That is one overhead. Similarly, in the very beginning, you just made sure that everyone is getting n by 4 amount of work. That is called load. I mean, dividing the load properly and giving it to all the processes. So the point is, in addition to this n minus 1 amount of work, you also have to do some extra work, and that extra work in parallel computing, and that the term which you use is called overhead. Okay, up to this point, everything is clear.
Yes, sir.
Okay, perfect. Now, okay, so now another thing which has to be noticed very carefully is that now if you look into this design which I have just given you, you can see that here I was just using one variable which was sum, okay, which was just sum, and then everything was getting added to sum. That I cannot do here, so I cannot just use one sum because I have to create private sums for everyone. So that is one another important point, so that can be found here. So what we are doing here is that each core divide in independent blocks, that we have done 4 blocks. Private variables, we have to introduce a private variable, let's say my sum. So this my sum belongs to each processor, to each core, okay, and then you get the global sum. So global sum is basically the sum of all my sums, and then you finally calculate. So here the global sum is your answer, which is a global variable. However, these my sums are private variables. So how many such my sums you have to create in this example?
4.
4. Yes. So 4 private variables you have to introduce, which are private to each of these thread or core. Okay. And another thing is that we have to do some overhead. So that part is clear. Another important thing is that this is not, I mean that, let me just show the next slide actually. So is it the only way to do this? This design, what I have shown you, the parallel design, is it the only way, or is it the best design, whatever I have shown? Not necessarily. So basically, the whatever you have shown, this method is a generalization of the serial global sum. Divide the work among cores, and then master core simply repeats the basic serial addition. So this is one design. Okay. So the point is, efficient parallelization is not a parallelization of each step of the serial algorithm, but devising an entirely new algorithm also. So let me give you another example. The same algorithms, addition of n numbers. I'm just giving you some another example. Let's say that I have numbers from 1 to, let's say, 12. Okay, so 1, 2, and so on. 12 numbers. So now what I decide that, let's say I just pick the first 4 numbers, 1, 2, 3, and 4. And then I ask, let's say this is my processor 1, this is my processor 2, processor 3, or processor 4. Now I ask them that P1 and P2 you collaborate together, and whatever sum you are getting, just pass it to P1. So let's say this is I'm calling it S1 now, which is sum 1. So S1 is basically the sum of 2 numbers, 1 plus 2. Similarly, 3 and P3 and P4 will collaborate, and then they will add this. So then they will write it here S3, which is S3. So this is like S1 in this case is equal to 3, and S3 here is 7. Okay. Then again I take the next 4 numbers. So I take 5, 6, 7, and 8. Again, these 4 numbers are taken like that: P1, P2, P3, 4, 4. So once they have completed this, they come to the next 4 numbers. Again, P1 and P2 collaborate together, then they add whatever they get, and then they add it to that S1 which is already present. So S1 plus this, so which is like 11 here, and 7 and 8 again collaborate together, and then they add whatever is already there, S3 plus this 15 here, and subsequently you can go down, and finally we'll go get the answer. Okay, this is another design. All of you agree? Is there anything wrong in this design as far as accuracy is concerned? You are finally going to get the answer, right? All of you agree?
Yes, sir.
Yes.
Yes. Yeah, so only thing is at the last end, so it is, if you really look into the design, so this is something like this. I mean, P1, P2, P1, P2, P3, P4. So they all collaborated, and finally somewhere you will get where only P1 and P3 will collaborate, and then they will give you the global answer, because you are storing the result in one of them. So you can see P1, P2 collaborating, storing in P1 maybe, and P3, P4 collaborating, storing in P3, and this will continue. And finally the partial sums will be with P1 and P3, and they will just together, they will collaborate and give you the answer. And if you look into it carefully, again the number of computations will be same actually. It's not going to be more. But if I have to compute, if I have to just compare these two design of two different parallel algorithms, which one will you choose? So one design is this one. So just look into the design very carefully. So in this design, what you are doing is like in the very beginning, you are giving n by 4 numbers to P1. They are not communicating with anyone. They first complete their task, whatever task has been given. So basically they do n minus 4 minus 1 operations. Then they calculate the partial sum. And finally, when all of them have calculated their partial sums, they just do one communication with each other. And then there is, let's say, P1 is the master node, and then it just combines all the results and get the answer for you. Whereas in this design, from the very beginning, I mean, they started communicating with each other. So because now they are operating on single number. So P1, P2 communicated with each other in the first step itself. They just added two numbers, and then they kept on communicating until you get the final answer. So which one you will choose?
So I have a question here.
Yes,
Like for 1 and 2, we get S1, and 3 and 4, we get S3, right?
right.
In that case, S1 and calculation of S1 and S3 are like in happening in parallel or not?
No, so it is like first they communicate. So P2 first gives the number to P1, let's say, okay, okay, and then P1 probably adds it. But so what I'm saying is P1 has only one, P2 has two, P3 has three, and P4 has four. The data, okay, and then P2 first gives the data to P1, and then P1 does the addition. But P1 has to communicate with P2 to get the data itself. You
Okay.
got it, right? Yes.
Yes.
So the point what I'm trying to emphasize is that this is more of a visualization. You can visualize any algorithm in this way, that you start communicating in the very beginning, and gradually you get the answer, and you will get a correct answer here also. But the main difference between these two design is that in one design you are doing very less communication, in another design you do a much bigger amount of communication. This part is clear?
Yes, sir.
Yes, but as far as the total amount of computation is concerned, total amount of computation, they are more or less same actually in both the cases. It is of the order of n or n minus 1, whatever we have calculated, and it is also of the same order like serial algorithm. So in all the cases, we will be doing of the order of n. Okay, so this part is clear. So the point is, even for a simple algorithm like addition of n numbers, I can design several algorithms. Okay, so, and we have to design the best one. Now, why I am doing all this discussion? Because I want to introduce a new term for you. That new term is called granularity. Okay, now what is granularity? Granularity is basically a ratio. So this is a ratio of computation to communication. So how much computation you are doing and how much communication you are doing. So it's a ratio between computation divided by communication. Now look into this carefully. So in these two algorithms, uh, where this ratio is high, in this case or in this case?
Case 1.
Case 1, exactly. Case 1, the computation to communication ratio is high because you are doing more computation compared to communications, because you are just doing 4 communications at the end. But here you are doing a significant amount of communication. From the very beginning itself, you have started communicating, all the processors have started communicating with each other. So based on this pattern, actually, there are two kinds of granularity. One is called coarse granularity. So coarse granularity is large amounts of computation or computational work between communication events. Fine granularity is like small amounts of computational work between communication events. So basically what we can say is that this is a coarse granular, probably this is a coarse granular, and then this is very fine. I mean, from the very beginning you have you have just given one addition. For one addition you are involving two processes. Okay, so this part is clear, this concept of granularity. What is granularity? All of you, this part is clear?
Yes, sir. Yes, sir.
Okay. So it is like two ends actually. So at one end, it can be very, very coarse. At one end it is very, very fine, and somewhere in the middle. Now the point is like, there is no simple I mean recommendation that you have to always coarse will be better than fine, or always fine is worse than coarse. I mean there is nothing like that. I mean there are algorithms where fine can be better than coarse. So there is an optimum level actually. I mean in some algorithms maybe it's better to take a very coarse granular algorithms, and in some cases if required it can be very fine as well. But overall the concept of granularity is clear to all of you, right? So this is the main concept. I mean ratio of computation to communication. We'll again come to this concept in our future lectures, but just remember this term now, very important in parallel computing: granularity. So a couple of terms to be remembered, very important. One is dependencies, and second is granularity, and third is concurrency. Okay, now let's talk about the overhead, which we have already discussed. So what kind of overheads we are talking about? So the overhead is basically the time required to coordinate parallel tasks, which is not at all present during your serial algorithm. Okay, this time which just goes for coordination purpose, you are not really doing actual useful work actually. So even if you look into this algorithm, the actual useful work was here actually, this 4n minus 4 4 into n by 4 minus 1 and this addition. But then you have a lot of communications here. I mean, so you did some extra work which is for coordination. In the beginning you just divided the work among all processors. So these are not the real work, but these are like extra work which you have to do to make those parallel algorithms. So typically, this parallel overhead includes several such works. One is like task startup time. So you have to introduce several tasks or several threads, whatever way you look into this. You have to introduce synchronization. Okay, you will require data communications. Yeah, then there are software overhead imposed by parallel languages, because now we are not going to do the same kind of compilation. The process of compilation will itself change. You need to introduce new libraries. Okay, so you have to include some extra header files probably. So and then there is a task termination. Finally you have to kill all the tasks or all the threads. You have to terminate the threads whatever you have introduced into your code. So the summary is that in parallel computation, in addition to the useful work, you will be spending a significant amount of time in overhead. Okay, so that's the important message. Okay, so to summarize, always a better algorithm is possible. So you can always come up with a very simple design, and then you can improve that algorithm. But these are the three important things which we always need to keep in mind if we want to improve our parallel design. The first is communication among the cores as least as possible. Load balancing, proper load balancing has to be done. So it is like, if you have total n works and 4 processors, make sure that everyone gets the same amount of work, which is not always possible, but we should try to do that. And then synchronization. So what do we really mean by synchronization? If you look into this simple example, at this point you have to make sure that everyone has calculated their part of the sum. So this is a local sum involved here, local sum involved here, local here, and local here. So before you do this addition, that is P1, P2, P3, P4, you have to make sure that everyone has completed their job. So we need to synchronize at this point before we do this part actually. So that is called synchronization. Okay. Up to this point, everything is clear. Everything is clear up to this point. Any doubt?
No, sir.
Okay. Perfect. Now, we'll be looking into a couple of matrices which are very important metrics in parallel computing. So the two important matrices are speed up, and the second one is efficiency. Okay, so first I will give a very brief introduction to speed up and efficiency, and then we'll have a more deep understanding of speed up and efficiency. So let's say that you have only one core. So that's like a serial algorithm. And what is the time to execute your algorithm or code actually? So let's denote it by T1. So that is execution time with one core or one processor, or basically the serial code. And this TP is the execution time with P processors. So if you have P processors, how much time it will take? So typically speed up is actually execution time on the serial divided by execution time on the parallel. Okay, so remember, it is the serial divided by parallel and not parallel divided by serial. So there should not be any confusion. So serial is on the numerator, and then you will get some number. And typically, uh, currently I'm just representing this speed up as a function of number of processors. Okay. Now, and when you define efficiency E, so that is like how much speed up. I mean speed up divided by process. So ideally, if you have P processors, you will like to have P speed up. That's the ideal situation. So it is like if one worker take 10 hours, 10 worker should take 1 hour. That's the ideal scenario. Now, ideal scenario will happen only under certain circumstances. Okay, so ideal world, if in the ideal world, it should be speed up is equal to number of processors, assuming there is a perfect scaling P times with P cores, and work is fully parallelizable. This is important point actually. I will come there. And then there is a constant workload. So the total amount of work which you are doing is same in both. I mean serial as well as parallel. So it should not be like for serial I am doing n amount of work and for parallel I am doing n log n amount of work. So then there is a different amount of work. Then you cannot get this ideal speed up actually. So under these assumptions that the code is fully parallelizable and the workload is also constant, you can get actually speed up is equal to the number of processors. Okay. Now the question is there any limit on speed up? What if we have infinite processors? What will happen if you have infinite number of processors? How much speed up?
Communication will be very difficult. I think so.
No, let's say that I have an ideal situation. So what will be the scenario in this case if you have infinite number of processors?
So time taken will be zero for P processors execution time.
Yeah, exactly. Execution time will be almost zero, right?
Yes.
Yeah, assuming that everything is parallelizable and the workload is constant. So, and if you have infinite processor, it is almost like zero time because I have infinite processor. So, what will be the speed up?
Infinite.
Infinite.
Exactly. Okay. So the point is that if I just look into that way, then almost it is almost like infinite. But now we'll have a better look into this. I mean, why I am raising this question. Uh, uh, so to summarize, once again, I would like to emphasize that speed up and efficiency are not performance metrics. These are not performance metrics. These are some parallel computing metrics. Performance metrics already we have discussed, like this compute performance in gigaflops per second, memory access performance. So those are performance metrics. So not to be confused with these two things. So these are not performance metrics. Okay. Now let's try to answer this question. Is there any limit on speed up? Okay. So let's assume uh, the normalized execution time. So normalized execution time means, I mean, you have some amount of time, but I'm saying that let's assume that total amount of time is 1. So that's what I mean by normalized execution time. So I'm just saying that total amount of time to execute your code is 1. So normalized execution time for single core can be divided into two parts, S plus P. S is the sequential or serial part, P is the parallel part. Now let's understand it very, very carefully. So what I mean here, let's say I have a serial code. Okay, so I am talking about a single code now. This is the point actually what I am trying to tell you. Let's assume normalized execution time for single code. So that means I am talking about a serial code. So in serial code I have several things. I mean several lines of code or whatever. Let's say I have 1000 lines. Okay. Now, if you look into this code, there are certain part actually in this code which is not parallelizable. I mean, you have to do it sequential. There is no other way. So let's say whatever reason there's a dependency issue or whatever, so you have to do it serially. There is no other way. I mean, even if I give you infinite number of processor, you cannot do that parallelly, because you have to do it serially. And let's say that that part is S, and rest is basically P. So that is like purely parallel part. So I have a for loop or whatever, so that can be done purely parallelly. So this is P. Now, what will be the parallel execution time with n processors? Can someone tell me? So this is T1. T1 is S plus P is equal to 1. T1. Now I am asking a question. What will be the parallel execution time with n processors?
S plus P by N.
S plus P by n. Perfect. S plus P by n. So the point is that even if you give me n processor, I cannot utilize for this S part, because that S part is a serial part which cannot be done parallelly. So I can only utilize those n processors in the P part. So this is S plus P by n. So now if you look into this carefully, S plus P is equal to 1. So that means P is equal to basically 1 minus S. Okay, so that is exactly what I have written here. So the speed up is equal to 1 plus. So what is the speed up? We have already discussed in the previous slide. So the speed up is serial divided by parallel. Okay, so serial is 1, so that 1 I am taking from here, 1, and then the parallel you have already calculated, which is S plus P. P is 1 minus S, so I'm just putting it 1 minus S divided by N. Now, can you conclude something from here?
So
Can you
for
conclude? Yes.
infinite number of processors, also we cannot get infinite speed up.
Yes, that's another way to interpret it. But the important message is like the speed up is determined by what?
Sequential part.
Parallelizable part. Sequential part.
Exactly. The speed up is finally determined by the sequential part which is present in your code. That will finally decide the bound on your speed up. I mean, so basically the possibility of parallelization. Possibility of parallelization. Whether I should even spend my energy in parallelizing a code or not. So that possibility comes from this relation. The possibility of parallelization. Okay. So this is actually captured through a very famous law. That law is called Amdahl's law. It is almost like the most important law in parallel computing. Okay. So what Amdahl's law states? So Amdahl's law states that the potential program speedup is actually can be captured using these formulas. So this is the potential speedup: 1 divided by 1 minus p. Exactly what I've written here. Actually, you can get the same thing here. Okay, so 1 divided by 1 minus p. Okay. Now let's say that if none of the code can be parallelized, if p is 0, so suppose you have a code, nothing is parallelized, p is equal to 0. So what is the speed up? 1, right? No speed up. Now suppose 50% can be parallelized. 50% of the code can be parallelized. So what is the maximum speed up you are going to get?
2.
2. Even if I give you infinite number of processors. That's the point. Even if I give you infinite number of processors, if only 50% of the code can be parallelized, you cannot get anything beyond 2. Okay. So what is the theoretical maximum speed up? Theoretically.
Infinite?
Infinite. Yes. Theoretically infinite, because p can become 1. This is a fraction. Either p can be 0 or it can be take a value between 0 to 1. If p is equal to 1, then you get an infinite speed. So theoretically, yes, I mean maximum speed up is infinite, but in reality actually there is always something which has to be done serially. So even if that number is very small, so even if s is equal to 0.0001, but I can clearly see that there is a bound, actually there is a limit how much you can get. This part is clear to all of you?
Sir, I had a small doubt.
Yes.
Sir, in the part where it is written that the fraction of code P, so how do we determine that fraction? As in, is it the number of lines in the code or something
No,
else?
no, 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 no. So this is like, I mean, there are two ways. One is like we have already done profiling. Okay. Now let's say that you have, let's say, I'm just giving a very ideal situation. Let's say that I have 5 subroutines or 10 subroutines. Okay, and then you figured out that 9 of the subroutines are absolutely parallelizable, or whatever subroutines function, whatever you call it, and one is not parallelizable. One is not parallelizable. Okay, and the profiler will actually tell you that how much time you spend on those 9 subroutine and how much you spent on that one particular subroutine, right? This part is clear.
Yeah, yes, sir.
And from there I can get the fraction. So because you are doing the profiling on your serial code, so the step one is like you do a profiling on your serial code, profiling on serial code. Okay, and then you know as a programmer that what is parallelizable and what is not parallelizable, because that I mean, there are tools, actually very sophisticated advanced tools, and a lot of research is going on in that area, that there are automated tools which tells you actually how, where parallelization is possible. Otherwise it is a programmer's responsibility to figure out, and that decision can be taken by doing dependency analysis primarily. So let's say that you have figured out that out of 10 subroutines, 9 subroutines can be parallelized and one cannot be parallelized, and now I have a breakup time. Let's assuming that each subroutine takes a point 1, point 1. So total I have 10. So total normalized, I'm just talking about normalized unit. So each one of them is taking 10. So total amount of time is 1. So now I know what is S and what is P. So what is S in this case? Only one
Point
subroutine
one.
cannot be parallelized.
Point one.
So how much is the S?
Point one.
Exactly, point 1. And how much is P?
Point
Point
nine.
nine.
Point 0.9. What is the maximum possible parallelization? Maximum speed up you can get?
10
Point.
times.
10 times, because you have to simply remember this formula, 1 divided by 1 minus P, or you can use this formula. The same, the formulas, both the formulas are actually same. You can check it. Okay. Okay. So now, so this part is clear. That answers your doubt.
Yes, sir. Thank you.
Yes. Yeah. So that is one way to do. Another way is like you can always use some tools to actually calculate the number of, if you don't really want to do a profiling on time, actually, you can do how much computations you are doing, like how many additions, how many multiplication, whatever. And then you figure out that which of those can be parallelized, which cannot be parallelized. And from there also you can get a rough idea. But this is a good way to do, actually, because it will actually give you a good picture. Okay, this is more like an experimental way, I mean, real life way to do this. Actually, do a profiling. You exactly know about your code. I mean, what is going on, and then you can figure out. But once again, just remember this is the uh, possibility of parallelization. Okay, because there is a big limitation of this law. Actually, I will come there gradually. That what is the limitation of this law? But this is a very powerful law, in fact, which can always be used in the very beginning when you are trying to parallelize. Okay. Okay. Now let's look into this picture. So here what we are doing, now let us introduce the number of processors, because if you simply look into this formula, actually 1 divided by 1 minus P, I have ignored the number of processors here. I'm just assuming that there is infinite number of processors. So if, with that assumption, this is the formula. But now let's be more practical, and now let's bring back the n, actually, which is present here. So here, if you look into this relationship, you can see that this n is actually present. So because if you make this n infinite, then what you get is like 1 divided by s. If you make this n infinity, and then 1 by s is nothing but 1 by 1 minus p, and that's how we got this, actually. So that is what I have written, 1 by 1 minus p. But now I'm saying that let us bring back that n, which is a realistic number n, and then let's see what is happening. So one way is like, first let us look into the left part. Actually, let's again assume that there are infinite number of processors. So and then in the x-axis, what I have done is like we put how much portion of the code is parallel portion of code. I think this is not clearly visible. So this is like 60, 70, 80, 90. So you can see that if there is a 90% code is parallel and I give you infinite number of processor, then the maximum speed up you can get is 10. Now in this picture on the right hand side, what we have done is like we have got both the information. We have the number of processors, okay, and we also have how much portion of the code is parallel. So that is being represented by these different colors actually. So now let's talk about a code. Let's say the yellow one. Let's say this yellow one where 90% of the code is parallelizable, and then I give you different number of processors. So first I give you 2 processors, then I give you 4 processors, and then I 8 processors. So still this point you are happy because you are increasing the number of processors and your yellow curve is going up. Your yellow curve is going up. Your yellow curve is going up. I keep on giving you 8, 12, I mean 32, 64. The moment I give you more processors beyond 64, you can see you get a saturation. I keep on adding number of processors and you don't get any speed up. Why? Because of this number. This number is 90% here. So because if I keep this p here, so p is 90%, which is p is 0.9. Okay. So finally what will happen is like if I keep on increasing my n, so p by n will keep on decreasing, it may go finally go to 0. So finally it becomes 1 by s. So s is 0.1 here because that is s is 0.1. So 1 divided by 0.1, so that is like 10, and that is where you are saturating. You can see the saturation at 10. You are saturating at 10. This part is clear to all of you?
Yes, sir.
Yes, sir.
Everybody, this part is clear, right? Any doubt before we go to the next slide? Okay. So let me quickly summarize that this Amdahl's law gives us the possibility of parallelism. We can always use this law to understand how the speed up will increase as we increase the number of processors, and at what point it will start saturating. And then I can get a very clear picture. Another picture which is coming very clearly is that if there is a very limited amount of parallelism present, let's say 25%, then you can see that you reach saturation with very few processors. I mean, even with 4 processors, probably you are saturated. After that, even if I keep on giving you more number of processors, you are not going to get any benefit out of that. So this tells a very important message that it's very important to do a profiling in the very beginning, whatever application you try to develop, that how much is the possibility. Because generally what happens most of the time, you will find the S is actually a very small number. I mean, a good code, I mean, it can be parallelized. Either it is like 0.001 or 0.01, something like that. So major part can be parallelized in most of good applications. But then there are applications where ACE is significant. I mean, it can be 2, 3, 4, 10, and then you can see that there is a big limitation if your application is something like that. Okay. Now, let me bring in overhead part. So till now, whatever we have done, whatever I mean discussion we have done in terms of this law, this Amdahl's law particularly, at no point we have considered overhead. But in the very beginning, we discussed that there are overheads. In fact, there are always overhead when you are talking about parallel computing. So now let's bring that and let's do a better analysis actually. So let us bring back the overhead also. So now what we are going to do, we are going to write this in a more generic way. So let's say I am going to introduce a new time. Let's say sequential computation time. Sequential computation time. And let's introduce 2 important variables here. 2 important variables. Okay. So one is n. Okay. Or let's denote it by small n. And another is p. So n is the problem size. Problem size means, let's say you are doing addition of 100 numbers or 1000 number or 10,000 numbers, so that is being captured by this n. That is problem size. The p is number of processors. P is number of processors or cores, whatever. Okay. Now, if I'm just talking about sequential computation time, let me denote it by sigma. So sigma should be a function of what? N, only n, or both n and p?
Only n.
Only n.
Only n. Exactly. Only n. Sigma is a function of only n. Okay. Now, let's introduce another thing. Let's call it parallel computation time. Okay. Parallel computation time. So by parallel computation time, I mean that can be executed parallel. Parallel computation time mean that can be executed parallel. Look into this sentence very carefully before answering. Parallelly. Okay. So what I am saying is that parallel computation time is the time that can be executed parallel in a serial code. So let's denote it by say phi. So phi should be a function of what? Only n or both n and p?
So both N and
Function,
P.
function of n and p.
Again, look into the sentence very carefully. So what I am saying is that there is a code. Okay, there is a code where there is something sequential, which is sequential computation time. I am saying that that time is always sigma e. Now I am saying the parallel computation time in the same code. So in the same code that can be executed parallel. So that should also be a function of n, right? Because p is not coming into the picture till now. I'm just saying that parallel computation means that can be executed parallel. Whether I'm doing it really parallelly, that is not. I'm not asking that. I'm saying that parallel computation time means the time which will go in that part actually, which can be executed parallel. This part is clear to all of you?
Yes, yes.
Yes, sir.
Yes. Yes. Now let me introduce an overhead. So basically what I'm saying is I'm talking about a design. And let's say I'm talking about a design. Let's say these are the four numbers I want to add. So this is one design. Okay, if I go by this design, I will get the answer here. Okay, now in this design, there are certain things which can be done parallelly. Let's say these can be done parallelly. Okay, and then there are certain things which has to be done sequentially. So I'm just talking about that thing. So in this so I'm just telling that there are things which can be done parallelly, which depends on n, and then there are things which can be done sequentially, which depends on n, not p. Now I am introducing a overhead. Now I am talking about parallel overhead. Parallel overhead. So overhead will only come when you have a parallel program. Okay. So these two I can always combine these two. So basically what I am doing is on a sequential on a single processor. Sequential on a single processor. Okay, so how much is that? Sigma n plus phi. All of you agree, right? Sequential on a single processor. All of you agree? This part? All of you agree with this statement? Hello?
सर
So
can
can
you
you
repeat?
repeat, please?
Yes sir. सर क्लियर
Yes.
नहीं हुआ कैसे किया?
Okay. I will repeat once again. So before we go to this statement, let us first complete this parallel overhead. So now I am introducing a new term and I am calling it parallel overhead. Let's introduce it by k. So k is going to be a function of n or both n and p.
Function of n and p.
Yes, because this is parallel overhead. It has to be a function of n and p because this is parallel overhead. Okay. Now I am just talking about a single processor, sequential execution on a single processor. So that should be only sigma n plus phi n because there is no parallel processing here. So I can remove this k n plus comma p. I should not include that. All of you agree?
Yes, sir.
Yes, sir.
Yes. Right. Now, what will be the parallel execution time? Now, I'm writing about the parallel execution time uh, for, for, for the parallel code. Okay, because this is a little bit probably got confused, but I made it very clear that can be executed parallelly. Parallel computation time is of the serial code. I'm talking about the serial code actually here. Okay. Now, what will be the parallel execution time for the parallel code?
Sum of
Sigma
sigma
plus
Sigma
K.
Sigma n?
sigma phi k
No,
plus phi n.
parallel execution time for the parallel code on, let me add a little thing on P processors. Let me add that also. Now you tell me clearly.
Uh, phi n p. Phi should be np
Phi, phi n,
divided by p, something like that.
phi n divided by P. Okay. And then anything else?
Knp plus knp.
Plus K n P. Yes. So this is the serial part which cannot be done parallelly. So that is this part, which so it is clearly written sequential computation time. I cannot do it parallelly. Second part is parallel computation of the serial code. So that can be executed parallelly. So that is the phi n part, this phi n part. So that can be divided equally. Let's say it is equally divided. So that gets phi n divided by P. Plus you have to introduce the overhead, which is K n comma P. All of you agree up to this point?
Yes, sir.
Okay. Now let me write down the speed up again. Speed up. Now what will be speed up? In terms of sigma and phi and k, what is speed up?
Sigma n plus phi n divided by sigma n plus phi n by p plus knp.
Exactly. I mean, there is nothing to worry. I mean, sigma n plus phi n, which is serial time, divided by parallel time, which is sigma n plus phi n by p plus the overhead also I include. So basically, this is serial divided by parallel. This is nothing but serial divided by parallel. Okay. Now, should I put an equal sign here, or this is more realistic, less than equal to? Which is more realistic and why?
Sir, maybe less than equal to, because you said that even though it is achievable, but it is very difficult.
Yes, this is more real. This is more realistic because the reason is simple. Because whether you can perfectly divide all the work among P processor, that is not guaranteed, right? Right. So assume that
Yes, sir.
someone gets a little more. So suppose suppose you want to do 100 additions and you have only 3 processors. So someone will get one more, right? Exactly, you getting my point, right?
Yes,
Yes,
sir.
sir.
So yeah, so this is like 33, 33, 34. This kind of division will happen. Everyone is not getting 33. Then only I can complete 100. So the point is, so this part will not become exactly phi n by p. So the point is, parallel portion of the computation, if you can divide it perfectly among all the processors, then this is equal to make sense. But otherwise, it should be less than or equal to. That depends on n actually, whether you are able to divide it perfectly or not. Okay. So let me write it down. So if not perfectly divided, if it is not perfectly divided, then speed up will be less. Speed up will be less. Okay. So the summary is I have to go ahead with this formula now, and then we can see something very interesting. So let me once again repeat it. So it is like speed up is equal to sigma n plus phi n, sigma n plus phi n by p plus the overhead, and overhead is a function of both n comma p. And let me denote speed up by psi, and now I can see that this is a function of both n comma p. Okay. So let me just go to the next slide and uh, understand the implications of this very important equation actually. So what will happen if we increase the number of processes? Now let's look into that first. what will happen if we increase p? Okay, so what will happen? Can someone tell in terms of computation and communication, what will happen if we increase p? Computation time
Will
Will
decrease.
decrease and saturate.
computation time decreases. I mean, just looking into the trend, actually computation time decreases, because you can clearly see here. I mean, you can, or let me write down that formula for you. So that formula is simple: psi n comma p is equal to sigma n plus phi n divided by sigma n plus phi n divided by p plus k n comma p. So now what I am saying is that if p increases, so I'm saying that increase p, so this part will come down, so the computation time decreases. This is my computation time. So this is computation, and this is the communication part. This is communication, this is computation, this is computation. Sigma n will have no effect if you increase p. Now what about the communication time?
Increase.
Yeah, so communication time will increase. Okay, now now let me take a case. Let us fix n, because I can see psi is a function of both n comma p. So I am changing my p, I am changing my increasing p. So let us first fix n. Fix n. So basically you are fixing the problem side. Fixing the problem side. Okay, and then what I'm going to do, I'm just going to analyze this actually. So let me see, say put execution time on the y-axis. Execution time on the y-axis, and the processor. So that is what I am changing. I'm increasing the processor. Let me keep the processors on the x-axis. Processors on the x-axis. Let's say that first point is 2, and the second point is 4, something like that, and then 6 and 8 and whatever. Okay. Now, now let me write it down like this. Let me just put the execution time here. So let me say this is the total execution time. Now for 4, what will happen? This should be a smaller bar, or it should be a bigger bar for 4.
Smaller bar.
This should be a smaller bar. This should be a smaller bar. No doubt about that. This should be a smaller bar. And for 6, it should be even smaller. Okay, this should be even smaller. Now, if I just focus on one of this time, let's say just focus on the case of 2 actually. So what I will see is that I have a small communication time. Let's say this is the small communication time, and the rest is computation time. Okay, so that's the breakup. So this is the total execution time. In total execution time, the little part is this, little part is the communication, and the rest is computation. Now if I come to the next bar, next 4 bars, so overall execution time has decreased, but what about the communication time? This should increase a little bit. All of you agree?
Yes, sir.
Yeah, so this should now become this. A little bit has increased, but computation time will go down, because that we have already written. The computation time decreases, communication time increase as you increase p. So I'm increasing p, so that is consistent. Again, if I come here, so then again what will happen? Again the communication time will increase and computation time will decrease. Up to this point, everything is clear?
Sir, I have a doubt that like how can we like 100% say that it would decrease only, because if the communication part increases so like significantly, so the graph could increase as well, right?
Exactly. That's what. That's why the fourth bar I have not done till now. Fourth bar I have not done till now, right? So till now this part is clear. Up to this first 3 bars, all of you agree?
Yes, sir.
Yes, sir.
Okay. Now let's look into the fourth bar. So the fourth bar. Now what will happen to the fourth bar? Probably the communication time will increase significantly, right? Although computation time will decrease, but that can take the overall time to a bigger than this case. So now what will happen? This part may decrease further. The computation time may decrease, but communication time may increase. and that will take the total execution time to a higher level compared to the case 6. All of you are getting this point?
Yes, sir.
Now what will happen if I make it even further 10? It should become even bigger.
Yes, sir.
Okay, and this computation will again decrease. I mean the communication will be, now we will take the maximum. I'm just giving a simple representative example. Now if I look into this plot actually, and if I join these things, so if I let me join these numbers, okay, and I will get something like this. Okay, all of you understood this part? Before we go and do and analyze this, all of you understood this?
Yes, sir.
Yes, sir.
Okay, now the moment you see such kind of plot, like something is this kind of plot, for what kind of typical interpretation you should do?
Where is the minima?
Exactly. So whenever you look, either you look into this plot or this kind of plot, we should always make a conclusion in terms of where is the minima, where is the maxima. So what is the good conclusion from this curve?
6
That
process.
it is best to have 6 processors with this.
Yeah, can you generalize? The 6246 is just an example. So can you generalize the conclusion?
So we can say that the number of cores or the number of processor where this graph has a minima is the efficient number of processors for our code.
No, everything is not captured in the statement actually. So
And
look into this.
this
So,
this optimal number of processor will be finite number.
okay, let me again make a boundary of this whole information, and then just give a one sentence to summarize this information, what is captured in this box.
The
For
middle point, the median.
Hmm.
for a particular size, problem size, there has
Exactly,
to be
exactly. You have to start from the first information, that for any fixed problem size. So there, from there I have to start. Okay, so let me first write for any fixed problem size, for any fixed problem size. Okay, now you can carry on. Now what is the conclusion?
uh, there has to be a optimized number of cores for the maximum speed up or minimum time.
Exactly, that's very good. So for any fixed problem size, there is an optimal number of processors or core, optimal number of processors. Okay, that minimizes overall execution time.
Time.
That minimizes overall execution time. See, this is very important for your assignments also. I mean, put all the information and then make interpretation, because that is the whole goal of these assignments. Because you will always have some kind of this kind of plots, like you change problem size, then you measure the time, and then make very good conclusions and interpretation, and that is where the learning is actually. So this is the important learning, that for any fixed problem size, so first you have to fix the problem size, because now if I keep on changing the problem size, I will not get this same plot. So first you have to fix the problem size, and then you can conclude that there is an optimal number of processors that minimizes overall execution time. This part is clear to all of you? Can I go to the next slide? This part is clear to all of you?
Yes, sir.
Okay. Okay, now so that's the first part. Now let's come to the efficiency. So already you have learned that efficiency is basically the measure of processor utilization. So you have already done that. Efficiency is equal to speed up divided by processor, that is number of process, speed up divided by p, and basically it measures the processor utilization. I mean, how long processors are being used on the computation. So if you are not getting a speed up of p, then there is definitely all the processors are not getting utilized properly. So let's say that if e is only 50%, let's assume that if e is only 50%, so that means that the processors are being used half the time on the actual computation on average. Okay. Now, so 100%, if your E is 100%, that is something which is desirable, that 100% efficiency. So that means that all the processors are being used on the computation at all times, and the speed up is almost P, because you will get 100% if speed up is equal to P. Okay. Now, what we are interested in is the range of efficiency. Range of efficiency, and again, efficiency will be function of what? Only problem size or both? Problem size as well as speed up processor. Let's denote efficiency by epsilon. So this should be a function of both problem size as well as number of processors. All of you agree?
Yes, sir.
Okay. Now can you tell me about the range of this epsilon? Epsilon range greater than or equal to and less than or equal to, what should be the range of epsilon? These are in percentage, but in terms of 0 and 1, right? All of you agree with this? All of you agree, right,
Yes.
with these numbers?
Yes.
Yeah.
Yes.
Now let's try to understand, I mean, from where these numbers are coming. So first, let me write down epsilon efficiency, and let me just write down this formula. So the formula is simple. So I have to just write the speed up first. So speed up, I remember, which is sigma n plus phi n divided by sigma n plus phi n divided by p plus k. Okay, k n comma p, and then I have to get this p here. So I have to multiply this p here. Okay, so if I write it like this, so this will become sigma n plus phi n, and then you can see p sigma n here, p sigma n, and this pp getting cancelled, so this is only phi n now, and this is again p k n comma p. Okay, now let's talk about the best case scenario. Best case scenario. Okay, so uh, what kind of code you will use? What is the best case scenario? I mean, in terms of number, what you would wish?
Hmm.
Yes.
I have a doubt that is K includes the communication time?
Yes, K is overhead. As I discussed earlier, this K is overhead. So it includes all kind of extra things, which is not computation.
Okay, okay.
Okay. Okay, so this part is my computation actually. Rest is all overhead.
Okay.
Okay, and you can see that sigma n plus, so in serial code you have only computation, no communication, no overhead. So sigma n phi n is also there. But here the only thing is it just gets divided among P processors. That's all. Okay. Now I'm just looking into a best case scenario. So when is the best case scenario? When you're as a programmer, what you will like wish in your code? The sigma n should be small or big?
Sigma
It
n is
should be
small.
small.
Yes. So if you're a best case scenario for parallelization, I'm talking about parallelization efficiency actually in that case sense. So you will always like that sigma n tends to 0. What about k?
That should be less also. मतलब
That should also tend to,
tends to be 0 only.
exactly, that also tends to 0. That should also tends to 0. And then what will happen if I now make both this 0? Then what will happen to epsilon n comma p?
1.
That will tend to 1. All of you agree?
Yes.
Okay, so that means I get the lower bound from upper bound from here. So best case scenario 1, when I can get 1 if sigma n tends to 0 and the overhead also tends to 0. So I design a code in such a way, or the algorithm is such that sigma n is tends to 0 and overhead tends to 0. And what about the worst case scenario? Sigma
Phi
n
n
tends to,
tends to
yeah, sigma n tends to finite. Okay,
phi
some
n tends
finite.
to 0.
Phi n tends to 0. Yeah, that's the first point. Phi n tends to 0, and then sigma n and kn are finite.
Finite.
Now what will happen to epsilon n comma p in this case? If finite means now
Finite.
look into this actually. If you make your p very high, So so P is also increasing. P is almost going to infinity. So what will happen to epsilon n comma P?
0.
Exactly, 0. So here you can clearly see that when I'm going to get the best case scenario and when I'm going to worst case scenario, because because finally when you are looking into efficiency, you are more concerned about what will happen if I increase the number of processors. So if you increase in this case, in the first case, best case scenario, if you keep on increasing the number of processors and you know that your sigma n almost tends to 0, kn comma p tends to 0, then your efficiency is almost 1 and you are going to get a speed up of almost equal to p. So you keep on increasing number of processors, you will get equal amount of speed up. Here what will happen is like, you know that there is no parallel part, actually phi n tends to 0, your sigma n is finite, kn comma p is also finite, and if you increase this p, then these two terms will go up actually, p sigma n and pk comma n comma p, and then overall the efficiency will go down and subsequently it will almost tend to 0. This part is clear to all of you?
Sir, I had a doubt.
Yes, yes.
Sir, if phi n is 0, then will it depend on P? Because if nothing can be parallelized, then how will it depend on P efficiency?
Exactly, phi n tends to 0. I'm writing phi n tends to 0.
No, I
Okay,
mean,
so that's
I
like
wanted to ask that if efficiency will depend on P in that case.
the efficiency always depends on p. If you look into this formula, see, if p is there, p is sitting here, p is also sitting here.
Okay.
Okay, but because if you look into it carefully, epsilon is equal to speed up divided by p. So I just put this p here, and then this p got cancelled actually. So you are just left with phi n here. Okay, this part is your doubt is addressed,
Yes,
I
sir.
guess, right?
Yes, sir. Yes.
Yes, yes, yes. Okay, so now let's look into another important thing actually. So actually, it is absolutely possible to again get that. I can do it quickly for you. Let me do that. Get that Amdahl's law back from here. So I can always write this here. So let me once again write it here. Psi n comma p is less than equal to sigma n plus phi n divided by sigma n plus phi n divided by p plus kn comma p. Okay, now Amdahl's law, if you remember Amdahl's law, that does not consider what it does not consider.
Communication time.
Overhead. Okay, now communication time is a part of overhead. Okay, so always tell it's not a good idea to just tell communication time, because there are many overhead. Although communication time is primary overhead, but there are many other overheads as well. Okay, so like
Okay.
synchronization is another overhead, load balancing is another overhead, so always tell overhead instead of just telling communication. Okay, so Amdahl's law does not consider overhead. So what term I should remove from here?
KNP.
KNP. So I'm just going to write this here, sigma n plus, I'm just going to remove the k term, and then I'm going to write psi n comma p. Now what should I write here? What should be the symbol here? Should I now still write less than equal to, or should I change that?
It should be less
Greater
than
than.
equal to 1.
How it should be?
Greater than. Oh,
How it can
and
greater than? You are
Less than equal to.
it should be less than, right? Because now you are removing one. So if this was less than equal to, now you're removing something, so which was actually a finite number, so it will be less than equal to, right? Because your denominator is less here. In this second case, your denominator is less. So if denominator is less, then it is guaranteed that it will be your total is even more compared to the previous case. So I should write less than less than. All of you agree, right? Okay. Now let me introduce a fraction. Let f denote. Let me write it. Let f denote the inherently sequential portion of the computation. Sequential portion of the computation. So what I'm saying is that f is the inherently sequential portion. So what I'm going to write, f is equal to inherently sequential, that is sigma n divided by sigma n plus phi. So that's the sequential portion. Okay. So I can always rearrange all these things, and then I mean that's an assignment for you. And if you can write it again, f n psi n comma p will become. Let me just write less than equal to. I mean, but otherwise it will be less than less than. You can check it. Sigma n plus phi n divided by sigma n plus phi n by p, and you can write it in terms of f actually now. So let me just do it here a little bit for you. So if I go in this direction, then it will be f sigma n minus sigma n, f sigma n minus sigma n is equal to f for f sigma n minus sigma n is equal to minus f phi n. Okay, and then if I just write phi n, because I want to get rid of this phi n, so phi n will become, I will take sigma n common. Okay, so that will become 1 minus f. Okay, and then f. Yeah, that's, I guess, fine. Yeah. Okay. Now, so this is fine, right?
Yes, sir.
Yeah, this is fine. Okay. So that is sigma n. I can write it in a better way actually. So that will become 1 by f minus 1. Okay. So now I just want to get rid of this phi n so that I will get a better relationship. So now what I'll write here is that sigma n plus sigma n plus phi n. So this is sigma n plus phi n. You can see this part here. This is my sigma n phi n. So that is exactly what is sitting in here actually. So I can write it sigma n divided by phi, sigma n divided by f, I can write. So that is coming from here. Okay, and for the bottom, I can write sigma n plus in terms of phi n. Now I can get this from here, this one. So sigma n 1 by f minus 1 divided by p. And if you do a little bit of manipulation, you will finally get this as, let me see, or I already did that. Yeah, so that is 1 divided by f plus 1 minus f by p. And this is exactly your answer. Okay, so this is like s plus 1 minus s by p, where p is the number of processes. Here p is number of processes, remember that. So it started with a very simple form of Amdahl's law. Again, we are coming back to there, I mean, with a more better understanding of that. And that is what you are seeing here. So the point is that the speed up, which is your psi, is finally being controlled by f actually, and that f is nothing but the inherently sequential portion of the computation. So this part is clear to all of you?
Yes, sir.
Okay. I think we can end it here. And if you have any questions, you can ask me now. I just stop the recording.